Hey, hi everybody, Team Grapevine. Again, talking about public detection and prediction using Twitter, now with Prettier Graphs at Twitter. We've got the rest of the cast and Justin Bieber as before. And just to give you guys a quick, to remind you guys again what we're working on, this is just a recap of our original thing, right? You get a bunch of things about Sony and about CS, right? And we want to try and figure out that there's some topic that's trending right now, Sony, Apple, this kind of thing, right? You guys remember this from last time. Except this time, we also throw in community detection, right? Because when you have different people talking about Justin Bieber, different kinds of people saying different things about it, so really there's sort of two thoughts of opinions about Justin Bieber, and we don't just want to combine them, we want to actually separate that out so we can predict each community separately. This was the basic idea we demonstrated last time. And why would you want to do this? There's many different reasons why you'd want to predict future word distributions. Some examples were, selling ads on Amazon, trying to do supply forecasting to figure out how popular something may be, doing load balancing on servers, so if you knew that there was going to be a trend in some particular area, doing stock price prediction, and then actually tracking actual Bieber fever through a social network of population. So this is all from before. So what's new this? Okay, this is also still from before. Again, we're kind of combining topic models and community detection. A bunch of these, mostly invented by Alex actually, and also some of these also with Alex on them. In fact, most of these, about 7 of these, are on Alex. But what's not is, I think, applying it to microblogging, but the scalability, also Alex covers, but microblogging at least, we can address that. And there's actually some really interesting things that come out that you would probably expect, but some interesting things that throw a wrench into the works of a lot of these that when you apply it to microblogging, but we'll talk about that at the end of the presentation. Okay, so let's talk about our pipeline. Okay, all right, so we have Twitter, right, okay, and we've been tracking the 1% of data. This actually turns out for the community stuff to be a lot more than our resources could handle, actually, so we didn't even need to use the 10% that we had, because this ends up being about 1,000K new users per day. And what we do then is we have a model that does kind of community detection. We've adapted some of the prior work on community detection that will take a social graph. This is just a subset. This isn't all of Twitter. But a subset of that and tries to figure out in a connected graph what are the different communities. So there's actually some connections here that you don't actually see. So we ended up with about 65,000 communities over the course of 5 days, right? So every 5 days you'll get a new 65K communities. And then we kind of naively parallelize this out into separate language models that include LDA and multinomial. We'll talk about that in a little bit. Okay, so.
All right. How do I use this?
Just one second.
Okay, so community detection. So community detection is about finding structures in large populations that can be usefully modeled as graphs. So the entities of interest are modeled as vertices in a graph, and the relationships you want to capture are modeled as edges between these vertices. So in our case, for Twitter data, the users are the vertices, obviously. The relationship we modeled is the reply to relationship. So if user V replies to a tweet written by user W, then we place an edge between these two vertices. So I mean, community detection actually applies more generally to people have applied it to a lot of things like to the internet, to social networks, and even to virus propagation. So at a high level, you're trying to basically segment this large graph, a graph with a large number of vertices and very sparse edges into subgraphs that somehow show the inherent structure of the graph. And you can think of it as a clustering problem, but you don't know how many clusters you have. You can apply traditional methods like spectral clustering, hierarchical clustering, and those methods have been found to work well for structured graphs. But for complex systems, the performance is actually not very good. So more recently, there is this work by Newman and an algorithm called Gervin-Newman, which really looks, instead of looking so unlike hierarchical clustering where you place high weights or you sort of introduce weights into your clusters that have a high weight, they look at weights that connect communities, right? So they talk about the betweenness of an edge. and they sort of rank order the edges by this weight, which is essentially the number of shortest paths that crosses this edge that connects communities. And simply by removing these edges, you end up with the communities. And that algorithm worked well for complex data, but it was computationally infeasible even for graphs that had a couple of thousand vertices. So later on, Newman and a couple more people came up with a more greedy algorithm, which used a different formulation. Okay, and this formulation is based on the intuition that within a cluster or within a community, there should be a high density of edges. And between clusters, there should be sparse edge connections. So, mathematically, they, simply compute the ratio of edges that fall within each cluster. However, this metric alone is not good enough because you can easily maximize this by combining everyone into a single community, and you would maximize this. This would just become one. Okay, so you want to have some sort of penalty term, and the penalty term they introduced is to consider how different is my graph from a randomized graph. So suppose I have completely randomly placed these edges. How different is my clusters, the edges within my clusters, different from this randomized graph? So. Okay, this doesn't work. Okay, so this term here basically accounts for a random placement of k edges that is simply the degree of vertex B and the degree of vertex W. So assuming that all those edges are placed randomly, well, how different is my my assignment of weights different from those randomized placements? So using this, they came up with a fairly good metric. And then they devised this essentially agglomerative clustering algorithm, which starts out by assigning individual communities to each user, and then start combining users. Okay, and each time they combine users so as to minimize or maximize this the decrease in this metric. Okay, in the end, they came up with a computationally feasible algorithm that scaled up to hundreds of thousands of nodes. So here's an example of the output of this algorithm. The algorithm is called the CNN algorithm. This is a snapshot of just 2 communities that was computed over a corpus of 5 days. So what we had in our hands was roughly 40 gigs of Twitter data that spanned a period of 30 days. And as Mark will go into later on, and as a lot of you have experienced, Twitter data is there's very little. Twitters only have so many characters per Twitter. So the data turns out to be quite sparse for the things we want to do later, like topic modeling. So we wanted to basically accumulate sufficient data for that purpose. But at the same time, the community detection algorithms we had on our hands, the state of the art, only scaled up to so many nodes. So it was a balance between what we can do at the first phase, that is community detection, and then what we can do later on using topic modeling. So this is essentially a visualization of the top, I think, 4th and 5th communities in that 65K communities that we found, basically ranked by the number of users. And and here's a plot of essentially the communities, the top N communities ranked by the size, and there's a pretty nice parallel distribution from this clustering algorithm. Okay.
Cool. Okay, so sort of a quick sanity check that we did was to say, okay, we have these communities, this is some representative samples, so who are these people that are very hub heavy? I'll let you guys take the first guess. In fact, what we do when we plotted just the first one that came up, we picked the center in it. There's 5 people that are bolded. Those are the cast members of One Direction, a British pop boy band. And then, of course, Justin Bieber is up there, followed by some Brazilian pop singers. So this tells us that the community algorithm is doing something reasonable. This is about what you'd expect if you would have picked the highest degree central people in these networks. So just to give you an idea of what's behind the cause of these, that's part of the cause. Okay, but let's look a little bit about the language that's used, because I think this has implications to LDA and other language modeling. as it applies to Twitter. So for instance, this is the frequency of number of words per tweet. So if your sort of standard LDA document is, even for a scientific abstract, you're going to have words that are much higher than this. I mean, on average, right, you're talking less than 10 for the majority of Twitter. So this makes language modeling quite interesting in the fact that, you know, n-grams don't really work here because people will use different grammars, you know, people will shorten words. You can't even use a standard vocabulary because people will shorten things. We found the term belieber, which is somebody who believes in Justin Bieber, was more popular than the actual term believer. So these kind of things make Twitter language very, very interesting. And so we looked at sort of two simple models of language just to kind of start to deal with this data.
So the simplest was bag of words multinomial model, where you assume the wording of words is not meaningful. So for one document, which is one tweet, it's composed of multiple sequences of unigrams or die, and it's generated from this multinomial parameter theta c, which is specific for each community. So we learned this theta c multinomial parameter vector for each communities. So this is the bag of words model. So we have parameters for indexed by community and also by the word in the dictionary. And since we made the independent assumption, we just multiply all the parameters together, and this is just a normalizer making it the probability distribution. And then to get the parameter vector for community, say C, we did math estimate. Given we have observed the community index, let's just call it capital C, we can maximize over the probability distribution to get the multinomial parameter on this specific word and community. And we also did we also got a list of stop words, and this is the visualization of the top 1,000 words from the largest community that we found. And these are some of the stop words that we don't learn. We just set the probability mass on the stop words to a very small number. I think I set it to the -10 or something. And I think it sort of makes sense that we get reasonable numbers out of the multinomial regulatory model. And Mark will talk about LDA.
Yeah. So again, LDA, it's kind of parallelized in the same way that we parallelize multinomial. We just have completely separate LDA models. Each one has completely different parameters from each community. So it makes it really easy to parallelize, but we can't really share statistical strength across samples. But this was just kind of as a baseline comparison against the multinomial model, just to see. There's obviously much more complicated language models, which we can get into if we have time, that try to tie together different communities. But this tends to be really scalable because we can just map out the documents immediately once we've done community assignments. What's an example of some kind of topics we get? Makes sense. This one tended to be a bilingual community that we had. So we actually have a Spanish cluster and an English cluster, and I think I don't know if this one or a different community actually had a Justin Bieber cluster. But yeah, this was just with 10 topics. For the LDA specifically, we did cross-validation to determine all the hyperparameters as well as the topic, number of topics against testing future words. So to get into the results, first question you could ask is, okay, communities, is it worth it? Like, why go through this stuff to get communities? So what we did was we looked at, if I have 3 people, right? 2 people that are in the community and 1 outsider. How similar is my word distribution to the person in my community versus outside of my community? And you plot that statistic. So if it was random, you'd expect it to be centered around 0, right? So being in my community tells you no more about my word distribution than somebody outside of it. Here we see there's a definite bias towards people within communities having similar word distributions to people within communities as opposed to outsiders. Right, so this tells you that there is some sort of correlation between being in a community and using the same words, which is kind of what we expected. In terms of the chaos, so what we're plotting here is now just looking between the language models within the community. So does it benefit us to do LDA versus empirical word count? Here we actually see that it's basically a wash. In some cases, LDA does better. Right here, we've just kind of ordered the community's ordering here doesn't really matter. It's just that we just ordered them by the margin between the KL divergence. So here you kind of see it's a wash. On average, the multinomial actually does better than LDA. Part of that is because the distribution in Twitter is like super peaked. So the vocabulary tends to differ so much across different people that any kind of smoothing you do can be kind of detrimental. Okay, so just to finish up some future work. So there's some interesting limiting factors about sort of the models that we're using. Right? I mean, they're very simple. They're just multinomial, standard LDA. There wasn't any fancy hierarchical Dirichlet processes or sharing clusters across communities. If you want to read any of those, just look at any of Alex's papers over the past 3 years, and you'll probably get all the information you should need. And again, this is only 1% of the tweet data, right? So we're not even given the full 100%. This has ramifications in 2 ways. First is you miss out on actual community connections, right? So if you gave me 100%, then we get a really good understanding of who's talking to whom, right? With 1%, we're only getting a fraction of that. Moreover, the 1% that you do get is a different user. There's no sort of, they don't give you the same 1%, right, over different days. So you can't even model the same people over time. So even if we look at 5 days and then we look at the next 5 days, you can't really tie together communities over time, which was something that would be nice to be able to do to sort of do any sort of recurrent Chinese restaurant process, looking at how communities change over time. You can't do that with the 1% data. There's other more advanced mixed membership community models. So the community model that we have here is just single membership, right? You're either in community 7 or community 8. But they also have stochastic mixed membership block models, which are kind of the rage nowadays. Also, you can read some of Alex's papers about this, or Eric Zing's papers at CMU talk about this. But scalability then also becomes a concern. Even with this sort of fast state-of-the-art community detection algorithm we have, it doesn't really scale up to Twitter like millions. It can do kind of 100K, but even now there's kind of issues getting the community detection up to that amount. So thank you guys for listening.